In this first exercise, we are given an extensive form game with perfect information without nature, and we are asked to provide its normal form, reduced normal form, and sequence form representations. Let us start with the normal form. Remember that in the normal form representation of an extensive form game, player actions are called plans, as they specify an action for each player information set in the extensive form. In this case, player 1 has 3 information sets, thus her plans are triples, where each element is an action available at one of her information sets. Specifically, the first element corresponds to information set 1.1, and it can be one among actions L1, C1, and R1. Similarly, the second element corresponds to information set 1.2, and it can be either action L2 or action R2. Finally, the third element is associated with information set 1.3, and it can be either action L3 or action R3. Conversely, player 2 has only 2 information sets, thus her plans are pairs, where the first element is an action available at information set 2.1, either L1 or R1, while the second element is an action at information set 2.2, one among L2, C2, and R2. Finally, all player plans are obtained by combining actions from different information sets in all the possible ways. For instance, L1, L2, L3 specifies action L1 at information set 1.1, action L2 at information set 1.2, and action L3 at 1.3. Let us now build player payoff matrices. First, notice that if player 1 plays L1 and L2, and player 2 plays L1, then the game ends in an outcome where player payoffs are AB, independently of how players behave in other enriched information sets. Thus, we can fill the matrix accordingly as in picture. If instead player 1 plays R2 rather than L2, player payoffs are CD. Similarly, if player 2 plays R1 instead of L1, then player payoffs are either EF or GH, depending on the fact that player 1 plays L3 or R3. Moreover, if player 1 plays C1 at information set 1.1, then player payoffs are uniquely determined by player 2 action at information set 2.2, and they are IJ, KL, and MN when player 2 plays L2, C2, and R2 respectively. Finally, if player 1 plays R1 at information set 1.1, then the game ends and player payoffs are OP. This is the complete normal form representation. In order to build the reduced normal form, we have to identify player plans that are equivalent, and thus they can be merged to form a new reduced plan. Here, equivalent means that such plans induce the same player payoffs independently of the other player plan. Note that if player 1 plays action C1, then the outcome of the game does not depend on how she plays at information sets 1.2 and 1.3, thus all plans that prescribe C1 are equivalent. Thus, we create a new reduced plan, C1 double star, where the stars denote the fact that actions at information sets 1.2 and 1.3 can be any. We can do the same with the plans where player 1 plays action R1. This is the reduced normal form representation. Let us switch the attention to the sequence form. First, we enumerate all player sequences. Remember that given a node in the game tree, we define a sequence by taking the ordered list of a player actions on the path from the root of the game tree to that node. As usual, each player has an empty sequence corresponding to the root node. Then node 2.1 defines sequence L1 for player 1. Node 2.2 defines sequence C1. And node OP defines sequence R1. Moreover, node 1.2 defines sequence L1 for player 2. Similarly, node 1.3 defines sequence R1. Node AB defines sequence L1, L2 for player 1. CD defines L1, R2. EF defines L1, L3. And GH defines L1, R3. Finally, nodes IJ, KL, and MN define sequences L2, C2, and R2 for player 2. These are all player sequences. Now, let us build the payoff matrices for the sequence form representation, where each entry contains player payoffs in the game outcome identified by a pair of sequences, if any. If player 1 plays sequence L1, L2 and player 2 plays sequence L1, then the outcome with payoffs AB is reached. Thus, we can fill the matrix accordingly as in picture. Instead, if player 1 plays sequence L1, R2, then payoffs are CD. Moreover, if player 2 plays sequence R1 rather than L1 and player 1 plays L1, L3, then player payoffs are EF, while they are GH if player 1 plays sequence L1, R3 instead. When player 1 plays sequence C1 and player 2 plays L2, C2, and R2, then player payoffs are IJ, KL, and MN respectively. Finally, if player 1 plays sequence R1 and player 2 plays the empty sequence, that is, she never plays, then player payoffs are OP. These are player payoff matrices in the sequence form representation. Note that the matrices are sparse, as payoffs are specified only for pairs of sequences that identify an outcome of the game. In all other cases, payoffs are zero. Finally, let us define the constraints that sequence form strategies called realization plans must satisfy. Let us start with player 1. We represent the constraints in matrix notation using the equation in the blue rectangle, where R1 is a vector containing a realization plan, which has one entry for each sequence representing the realization probability of that sequence. In other words, the probability by which that sequence is played. F1 is a matrix representing the coefficient of R1 in the constraints. It has a row for each constraint, that is for each information set, and a column for each sequence. F1 is a vector with size equal to the number of constraints, which contains constant terms of the constraints. Of course, the realization probability of the empty sequence must be 1. Now let us analyze information set 1.1 and the associated constraint. Given an information set, its sequence form constraint prescribes that the sum of the realization probabilities of the sequences entering the information set must be equal to the sum of the probabilities of the sequences exiting it. In this case, the empty sequence enters and L1, C1, and R1 exit. Here, for information set 1.2, we have an analogous constraint. Sequence L1 enters, while sequences L1, L2, and L1, R2 exit. An analogous constraint must hold for information set 1.3. These are the final constraints on realization plans of player 1. With analogous reasoning, you can recover the constraints for player 2 realization plans. In picture, you have the final result.